Madison College Building Construction for the Fire Service, Week 5, homework problem. I guess it'd be homework problem 7. Even though it's labeled as 2, it's the 7th problem you're going to encounter in the examples. This problem's got several elements, the first of which is calculating the moments, and it says about point O, but there's no point O in the diagram. And looking at the author's work on this, I believe he meant about point C. Now the first thing we're going to have to do to accomplish that is to get these vectors that are not acting in horizontal or vertical directions into horizontal and vertical directions. Because as you know, we have to get all of the vectors either parallel or perpendicular to each other to start canceling them. So remember that the way you deal with that is that you break the vectors, you resolve the vectors into vertical and horizontal components that you then stack up head to tail. So we've got several vertical and horizontal components. And actually I'm going to flip this guy around. Then the next step is you have to think about calculating the length of these. And so we'll start over on the right side of the diagram. And what is the length of this vector? Well, we can't say for sure without figuring out some angles. So let's look at angles here. We know that this included angle is 40 degrees, which means that this angle here is going to be 50 degrees, and this angle here has to be 40 degrees. Well, I'm going to work based off of this 40 degree angle over here. If this is the 40 degree angle, that makes this the side opposite and this the side adjacent. So we need to have something that relates opposite to the length of the hypotenuse and adjacent. So the opposite relationship is going to be the sine function, and the adjacent relationship is going to be the cosine function. So here you can see I've inserted the calculations for the forces on each of these vectors. This opposite side is developing a force of just shy of 129 pounds. The adjacent side is about 153 pounds. Now it'll be the same process for the angled vector on the left side of the diagram. So we have to figure out some angles, and let's think about what we know. We know that this angle is 50, which means that this complementary angle here has got to be 40. This angle by definition is 90, which means that this angle right here needs to be 50. So using 50 degrees as our working angle, that would make this the opposite side. This would be the adjacent side. And we'll calculate those the same way. We'll use the sine function to relate the hypotenuse to the opposite side, and the cosine function to relate the hypotenuse to the adjacent side. So you can see the process is the same of using trigonometric functions to relate the hypotenuse, which represents the composite force, as a horizontal and vertical component. Notice now that the multiplier of the trigonometric function is 100 pounds because that is the magnitude of the vector, whereas the first vector was a 200-pound vector. So here you can see, folks, I've diagrammed all of these forces, relative positions compared to the point about which we are trying to take moments. So each of these distances that you see represent distances from point C, either perfectly vertical or perfectly horizontal. Now, the next step involves calculating the moment about each of these, or created by each of these about point C. So you can see that I've added the sum of the moments operator here, and now I'm just simply going to calculate these and strike them from the list as they're calculated. So we'll start here with this one on top, and you'll notice that it is pointing to the left. It is a leftward force, and it is above point C. Well, that means it's going to generate a counterclockwise moment. So the counterclockwise moment is going to be a positive number, so it's just going to be 64.3 times 3 feet. And then we can strike that one from our list. So let's mark this one off to know that this vector is dealt with. Okay. Now, what's next? Let's take a look at this rightward vector. That vector is going to produce a clockwise rotation, so it's going to be a negative number, negative 128.6 times, what's its distance? It's 2 feet from C. Okay, and again, we'll strike that so we know that we're done with it. Okay, what's next? Let's take a look at this one over here. This vector is 3 feet from C, and it's pointing downward. It's going to have a tendency to produce a clockwise rotation, so again, that'll be a negative number, negative 153.2 times 3 feet. Okay, and on to this 100-pound vector. This one is pointing to the right. It's going to produce a counterclockwise rotation, so it'll be a positive number. It's 100 pounds times 2 feet. And again, we'll move on to this vector over here, this 200-pound vector. This is going to produce a counterclockwise rotation. This is going to produce a clockwise rotation, so it's going to be a negative number, and it's going to be negative 200 times its distance of 2 feet. And we'll strike that one, because we're done with that. And last but not least, this 76.6 pound vector, it is producing a clockwise rotation, which will be a negative value, and it is at a distance of 3 feet. So plus negative 76.6 times 3. So that's the sum of all of the component moments about point C. So here's a great tool for solving these types of problems. This is Excel, and you can see that basically I've just copied the text from the PowerPoint slide into the Excel program. And the great thing is that if I put an equal sign before it, Excel will calculate the value for me. So the moment about point C is negative 954 pound-feet. What does that mean? That means this thing wants to rotate in the clockwise direction with 954 pound-feet of torque. So let's just draw that label in. That's the first part of the problem. Clockwise moment, 954 pound-feet. So now that you've calculated the net moment, the second part of the problem asks for a net force calculation. So again, all you're going to do is just add up all of the x components and add up all of the y components. Let's again start with the first vector at the top, and you can see that that's 64.3 pounds to the left, so you'll notice that I've given it a negative sign. And again, I'll make a mark to indicate that yes, we've dealt with that vector. And let's look at this one to the right. This one to the right here is 128 pounds, and you'll notice that it is positive because it's to the right. Okay, so we'll mark that one off. And this vector over here, this downward vector, doesn't have any horizontal components, so we'll ignore it. This vector here is 100 pounds to the right. And again, it's a positive number because it's to the right, so let's mark that one off. And that is going to cancel. That is all of the horizontal components of these vectors. So now we just simply need to add these. Well, again, an easy way to do this is I'm going to just copy that text right into Excel. And I'm going to say equals, paste that text into Excel, and Excel is going to give me my number of 164.3 pounds. Now that the x components have been calculated, it's simply a matter of calculating the y components. There are only 3 of them in this problem. There's this one on the right that is negative 153 pounds, negative 153.2, and it's downward. And we'll mark that one as recorded. There's this 200-pound upward one. So again, we'll mark that as recorded. And then there's a 76.6 pound upward one. And again, that's a positive number because it's upward. Once again, the quickest way to deal with this is simply to paste this into Excel. And we get a net value of 123 pounds upwards. So, we could now draw these as components of an individual vector acting on the outside of this square. So what we've been able to determine so far is that if you added up all of the forces that were acting on this block, it comes down to an upward push of 123 pounds and a rightward push of 164.3 pounds. But just as we were able to resolve these individual vectors into vertical and horizontal components, we can do that process in reverse now and compose them into a single vector of a known length and a known heading. And we'll call that vector the resultant. So I've drawn it in red here. Think red, R for red, R for resultant. What's the length of the resultant vector? Well, this is simple Pythagorean theorem. It's 164.3 squared. That's the symbol that Excel uses for squared, plus 123 squared, and then we have to take the square root of the whole thing. So SQRT is how Excel looks at square roots, and that will tell me the magnitude of the resultant. So again, if I just paste this formula into Excel, we will get our number. Oops, can't have an equal on both ends. There we go. 205 pounds is the magnitude of this resultant vector. The last thing you're asked to find is the heading of the resultant vector. And if you think about what you know, we're trying to find angle theta as it's shown here in the diagram. You know the opposite and adjacent. So the function that relates opposite and adjacent is tangent, but normally the way tangent works is that you put an angle in and you get a ratio of opposite to adjacent out. And in this case, we want to put a ratio of opposite to adjacent in and get an angle out. So we need to use the inverse tangent function. It's the machine that undoes the tangent function. Now, Excel uses some interesting notation on this. Excel expresses angles in radians. And so the first thing that we have to put in is we have to convert to degrees. And then we're going to use the arctangent function, which Excel expresses as atan. And the arctangent is going to take the ratio of the opposite over adjacent. So 123, it's just 123 divided by 164.3. So the arctangent function is going to give an angle. The degrees function is going to convert that angle from radians into degrees. And again, if we paste this into Excel, we'll have our answer in short order. And so we find out that that angle is about 36.8 degrees. And we can even insert a degree symbol. So that's the conclusion for solving this problem. A single vector of 205 pounds magnitude at an angle of 36.8 degrees could produce this torque. Now, in looking at that result and looking at our previous result with a moment, it becomes clear that an upward and rightward force is not going to produce a clockwise rotation. And as I review the calculations, I notice that there's actually a sign error. This is actually a negative 954 pound-foot moment, so it's going to be counterclockwise. Beyond that, though, it is accurate. Now, the last part of this is going to involve figuring out where, from left to right, this resultant vector needs to act on the block to make that moment possible. And we know that that moment is negative 954 pound-feet, and we know that the position of this vector is negative 3 feet. It's 3 feet below point C. And so we can plug all of this into the equation and just using some algebra tricks, we can push this thing around